Welcome friends for the lecture on design of power screw. Now first, what do you mean by power screw? Power screw, it is a mechanical device used for converting rotary motion into linear motion and transmitting the power. You can see here in this picture, this is actually the power screw which you are using for the lead screw. And again in this slide you can see the thread profile. Here in this thread profile you can see the single start, double start and triple start. Now what do you mean by this start? Actually, you know there are two important terms in the screw. The one is the pitch and another one is the lead. In single start thread, generally the threads which we are using for the screw, it is a single start thread. So lead, it is equal to the pitch. Now pitch means what? If you consider one point on the thread profile and another point on the consecutive teeth at same position, and if you measure the distance along the axis, then that distance is called pitch. And the lead means if you turn the screw for one complete revolution, then the axial distance traveled by the screw, that is the lead. Now we know that if it is single start screw, if you rotate the screw in one complete revolution, the axial travel distance, it is equal to the pitch. But wherever we want more motion, that means lateral motion, then in that case we can use the double start or triple start thread. That means if you rotate the screw in one revolution, it will travel the distance 2 times the pitch, and in triple start thread it is 3 times the pitch, right? So now which are the thread profiles which we are using in the power screw? Mainly we use the square thread profile or trapezoidal or the buttress. All these are the basics of the triangular one. The first, it is buttress, it is the part of the triangular thread, and the square and trapezoidal, it is part of the square thread profile. Now there are two types, mainly the trapezoidal thread forms. One is the ACME, we call it as a ACME, and another one is the metric trapezoidal. And nowadays most of the time international standard organization is use this metric trapezoidal. You can see here in this diagram, see the square thread profile, the angle between this profile, it is 90 degree. Now this ACME or metric trapezoidal thread, it is a modification of the square threads. Here you can see that inclination is 29 degree, and the base, if you compare these two drawings, square thread and the ACME thread, then the base distance and in the ACME thread base distance, ACME thread braid distance is more, that means the width is more than the square thread, and that's why that becomes more stronger, right? And third one is the buttress thread. Here we can transmit the motion only in one direction and not in the other direction. So these buttress threads mostly we use only in that case where we want in motion in one direction only, right? So what are the application of this power screw? The main application of this power screw are as follows: to raise the load, like a screw jack. You know, in the screw jack, we use the screw jack for lifting the vehicle, right, to raise the load. Then to obtain the accurate motion in machining operation, whenever we require the threading on any part, that time in lathe machine we engage the lead screw, right? So lead screw of the lathe, that is the power screw. Then to clamp the workpiece, especially the vices, in vice we use the threads, that is the square thread mostly, and the screw which you are using, we call it as a power, because it presses to hold the job, right? And the fourth one, to load a specimen, that means in UTM, universal testing machine, we use this. You can see here the loading diagram, screw press application, the Y-size part, whatever the vertical part you can see here, that is actually the screw, right, power screw. And then there is a handle is provided so that you can apply the torque effort over there, and you can clamp the part which you want. Now here this is the example of the screw jack, where now the load is kept over the screw and then you are applying the effort at the bottom so that load can move up or down. Now here the most important part is whenever we are using the power screw, now first you have to see some analysis. Now always here there is a friction between the screw and the nut, right? The nut, it is the portion in which the screw will rotate. So you can see here in this diagram, this part, the part which is shown over by the shaded lines in the frame, that is the nut. That part is having the internal thread and your screw is having the external. So there definitely there will be a friction between these two. Now we'll take, for understanding, we'll take a simple example that screw is there. Suppose you have a screw and we know that the thread is, it is helical, right? Now if you unwound the thread, if you take a one complete thread and if you unwound it, then whatever the triangle here it is shown, see the P, it is the pitch, right, and this horizontal distance pi d, that is the circumference of the screw, mean diameter. When you take a mean diameter, pi into mean diameter, that gives you the circumference. Now the hypotenuse, that gives you the total length. If you unwound or if you open that thread, this hypotenuse, that gives you the length of that one complete thread. Now here that is inclined, so you know that the thread is inclined, so that is at helix angle alpha, right? So therefore it is written alpha p and pi d. Then phi, it is the friction angle, and mu, you know that it is coefficient of friction, and you know the relation between the friction angle and the mu, that is mu, it is equal to tan phi, right? Now from this triangle we can write tan alpha, it is equal to p divided by pi d. Now we know that, see, now if you consider here, suppose we are lifting the load, right? So just take an example of screw jack and we are applying certain efforts and your load is getting lifted. Now ultimately whatever the load you kept on the screw, that load will act on the threads of the screw, right? So this inclined surface, that is whatever the inclined surface shown over here, that is the surface of the thread, right? And whatever the load is acting there, that it is shown over, it is W, right? Now you can divide this W into two components, W cos alpha and W sin alpha. Why? Because one, if you draw a line perpendicular to this inclined plane, so inclination between these two lines is alpha, so that means this is also alpha, and the line which is parallel to the inclined surface, that is W sin alpha. Now we know that always there is a normal reaction, so Rn will act perpendicular to the whatever the box shown over here. Now we are applying the effort here, so that effort is P, right? Now this P also we can divide into two components, P sin cos alpha along the surface and P sin alpha perpendicular to the surface. And when this load, if it moves up above the inclined surface, then definitely there is a friction, right? So when there is a friction, definitely the frictional force will act in the opposite direction, that means in the downward direction, and that frictional force F, it is equal to mu into Rn, right? This you know, these are the very basics of the friction. Now if you resolve these forces along the plane, now you can see here in this diagram, this P cos alpha, P cos alpha, this is in the upward direction, right, parallel to the inclined plane, and in the downward direction parallel to the inclined plane is F and W sin alpha. So P cos alpha, it is equal to W sin alpha plus F, and F is what? It is the frictional force, so mu into Rn. So you can substitute here, so therefore you will get W sin alpha plus mu into Rn. Suppose this is equation 1. Now again we are resolving this perpendicular to the inclined plane. Now you can see the perpendicular to the inclined plane, there is one force, that is Rn, which is acting perpendicular to the inclined plane in the upward direction, and P sin alpha and W cos alpha, that is acting in the downward direction. So therefore Rn, it is equal to P sin alpha plus W cos alpha, right? Rn, it is acting upward, and W cos alpha and P sin alpha, it is acting perpendicular to the inclined plane, right, but downward, and therefore we can write Rn, it is equal to P sin alpha W cos alpha. Now we know that P cos alpha, it is W sin alpha plus mu Rn. So you can substitute, or P cos alpha, it is equal to W sin alpha plus mu Rn, and Rn, it is equal to P sin alpha plus W cos alpha. You can substitute this Rn value in equation 1. So P cos alpha, it is equal to W sin alpha plus mu Rn is P sin alpha plus W cos alpha, and if you solve this, you will get W sin alpha plus mu P cos sin alpha plus mu W cos alpha. So P cos alpha minus mu P sin alpha, this is equal to W sin alpha plus mu W cos alpha. You can take this P outside, so cos alpha minus mu sin alpha, this is equal to W sin alpha plus mu cos alpha. Now from this equation you can write P, it is equal to W sin alpha plus mu cos alpha divided by cos alpha mu sin alpha, right? Now we know that mu, it is equal to tan phi. Phi, it is what? Phi, it is the friction angle, and mu, it is the coefficient of friction. So if you substitute that tan phi, then you will get the equation P, it is equal to W into sin alpha plus tan phi cos alpha and cos alpha minus tan phi sin alpha. Now multiplying numerator and denominator by cos phi. If you multiply numerator and denominator by cos phi, then you will get sin alpha cos phi plus, now tan alpha means sin divided by cos, cos will get cancelled, so sin phi cos alpha, right? And in the denominator, cos alpha cos phi minus, again tan divided by cos will get cancelled, so sin phi sin alpha. Now sin alpha cos phi plus sin phi cos alpha means sin alpha plus phi. Cos alpha cos phi minus sin phi sin alpha means it is cos alpha plus phi, right? So sin divided by cos, you will get tan. So therefore you will get this equation P, it is equal to W tan alpha plus phi, right? This is the efforts in terms of the total weight to be lifted and the alpha and phi. Alpha means it is the helix angle and phi, it is the friction angle. Now the torque required to overcome the friction between the screw and the nut. Now this is the effort. So P into d by 2, right, the radius. So d by 2, P into d by 2, that means W tan alpha plus phi into d by 2. This is the torque required to overcome the friction between the screw and the nut. Now when the axial load is taken up by the thrust collar, so that the load does not rotate. See, whenever we are using the screw jack, when you are lifting, when you apply the effort, at that time your vehicle is not rotating, right? It will just move. So that means definitely with the screw your load will not rotate. So we are providing there some collar, right? That collar will remain stationary, and over that we apply the load, so that the load does not rotate on the screw. The torque required to, that means definitely the collar and the screw, there is a friction. So that friction, we have seen the clutches. In clutches, we have seen there are two theories, uniform pressure theory and uniform wear theory. So according to uniform pressure theory, this torque, it is, now we'll consider this, whatever the torque it is required to overcome the friction at the collar, that is T2, and that is equal to 2 by 3 mu W into R, and R it is the mean radius. According to uniform pressure condition, this mean radius it is 2 by 3 into R1 cube minus R2 cube divided by R1 cube R1 square minus R2 square, not R1 square, it is R2 square. And if it is uniform wear theory, then mu into W into again R, but that R is what? It is the mean radius, and that mean radius is R1 plus R2 divided by 2, right? So by this you can find out T2. So you will get T1 and then T2. So T1 plus T2, that is the total torque, right? So this total torque, now if P1 is applied at the end of the lever of the arm L, the total torque required to overcome the friction must be equal to the torque applied at the end of the lever. So P into d by 2, it is equal to P1 into L. Now this equation, that means this P into W into P equal to W into tan alpha plus phi, this we got when we are lifting the load. Now how much the effort required when you are this load you are taking down? That means the torque required to lower load by square threaded screw. Now in that case, what will change here? Only now your load is moving downward, so definitely the frictional force will act in the upward direction, right? So mu into Rn, that will act in the upward direction. So now if we again derive this, you will get the similar equation, P it is equal to W tan phi minus alpha. Now see the difference between these two. When you are raising the load, at that time you are getting P it is equal to W tan alpha plus phi, and when you are lowering the load, at that time you are getting P equal to W tan phi minus alpha. Now what is phi? Phi it is the frictional friction angle, and alpha it is the helix angle. Now if here phi, if it is less than alpha, then this will be negative, so P is negative. So P negative means what? You won't require any load to any effort to take a load down. That means automatically you will come down, and we don't want that. Otherwise what will happen? Suppose you are lifting the vehicle for removing the wheel, and once you leave that, it will automatically come down. So we have to avoid that. That means your phi should be always greater than alpha, so that the P it is the positive one, and again the same you will get. Now what is the efficiency of the square threaded screw? How to find out the efficiency? Efficiency of the square threaded screw may be defined as it is the ratio between the ideal effort and the actual effort. Now ideal effort means what? There is no friction, means friction angle will be 0, phi is 0. Now if the phi is 0, then the ideal effort, that will be equal to P into tan alpha plus phi. Phi is 0, means W into tan alpha, divided by actual effort, definitely there will be a friction, so W into tan alpha plus phi. So this gives you the efficiency, which is independent of the load. See, W and W will get cancelled, so efficiency it is equal to tan alpha divided by tan alpha plus phi to raise the load. Now in the above equation only screw friction is considered. However, if the screw friction and the collar friction is taken into account, see here in this equation we consider only the screw friction, friction between the screw and the nut. Now if you consider the friction between the screw and the nut and the friction of the collar, then the efficiency, this is equal to torque required to move the load neglecting the friction, and the torque required to move the load including the screw and collar friction. So here this TO, this is equal to d by 2 into PO divided by P into d by 2 plus mu 1. That means this mu 1 W into R, this gives you the torque required to overcome the friction of the collar, and this P into d by 2, this is the torque required to overcome the friction between the screw and the nut, right? Then now, as we discuss overhauling and self-locking screw, we have seen that when we are lifting the load, we are getting P is equal to W tan alpha plus phi. Now, even though there is phi is 0, there will not be any question, because definitely we have to apply, because tan alpha it is positive, so we have to apply the effort. But when you are taking down, that means when we are lowering the load, that time our equation is P equal to W into tan phi minus alpha. As I told you, if the phi is less than alpha, what will happen? The P will be negative, right? Now, if the P is negative, that means in the other word, the load will start moving downwards without any application of the torque. Such a condition is called the overhauling of the screw. If, however, the phi is greater than alpha, the torque required to lower the load is positive, indicating that the effort is required the load to take that down. Such a screw is known as the self-locking screw, right? So, as we discussed the efficiency of the self-locking screw, efficiency it is equal to tan alpha divided by tan alpha plus phi, right? So, for self-locking screw, that means phi is greater than or equal to alpha. So, the phi is greater than or equal to alpha, then approximately this tan phi divided by tan 2 phi, right? And this tan 2 phi, you can tan 2 phi, we know that 2 times tan phi divided by 1 minus tan square alpha, right? So, what you get? Tan phi into 1 minus tan square alpha divided by 2 times tan phi. Now, efficiency it is less than or equal to 1 by 2 minus tan square phi. From this expression, we can say that the efficiency of the self-locking screw it is less than 1/2, because 1/2 minus something, so definitely it is less than the 1/2, means less than the 50%. If the efficiency is more than 50%, then the screw is said to be overhauling screw, right? So that's why for the efficiency of the power screw, it is always less than 50%. Then the analysis of this ASME or trapezoidal thread, now instead of it is square, it is slightly inclined, so load will act, W will act vertical, so Rn it is inclined at angle beta, so Rn it is not now W into cos alpha, right? But in case of ASME, the normal reaction between the screw and the nut is increased, because the axial component of the normal reaction must be equal to the axial load. So therefore this Rn it is equal to W divided by cos alpha, semi angle of the thread, and the frictional force it is mu into Rn, and that mu into Rn means W cos beta. So this mu divided by cos beta, that we can write mu 1 into W, right? So mu 1 it is the virtual coefficient of friction. In design, again we required the which type of material we should use for the power screw. So most of the time we use the plain carbon steel such as 30C8 or 30C, 40C. Number of times in the number of design data book we write like this only, 30C, C40 or C45 this way, or 45C8, right? And sometimes we use where you want more stronger than alloy steel, but most of the time we use the plain carbon steel, and the screws are case hardened. So lead screw are case hardened by nitriding process. Here we have to design, most of the time we have to design the lead screw, because you are a student of production engineering, so more related to the machines. So bronze is an ideal material for the nut. So that means the material for the nut is the bronze, and the material for the screw it is plain carbon steel or alloy steel. But whenever we are using the material for the lead screw, it is the maybe plain carbon steel with the case hardened by nitriding process. So ideal material for the nut and the mainly tin bronze or the phosphor bronze are used for the nut, right? So this is the fundamental which we required for the design of the power screw. Now in the next lecture we will see how to design the lead screw exactly. Thank you very much and take care, friends.